Welcome back, Apologia, 8th grade physical science, week 19, day 1, textbook pages 316 to 320, notebook pages 261 to 265. Have you ever gone deep sea fishing or surfing? If you have, then you know how important it is to check the weather forecast. You need to determine if the waves will be choppy and too big to go out on a boat, or if they will be big enough to catch a good wave with your surfboard. We use several characteristics to identify and describe waves. You've already been introduced to the terms crest, the highest point of the wave, trough, the lowest part of the wavelength, which is measured in between two crests or two troughs, and amplitude, the height, as descriptive terms. But in this section, we'll discuss what we can learn about a wave's property using these terms and others. Amplitude. Suppose you are wading in the ocean at the beach. The amplitude of the waves would basically tell you how high the waves are. People riding surfboards would be happy if the waves had large amplitudes, because that would mean the waves would be high. People wanting a leisurely swim in the ocean or to take a boat out to fish would be happier with smaller amplitude waves. The amplitude of a wave is the maximum displacement of the medium from its rest position. All right, so this is its rest position. So the amplitude for this top high amplitude wavelength would be up here or down here. So it's from the rest position out to the highest position. Down here, we have the rest position, and it's a lower amplitude, so it would just be from here to here or from here to here. Transverse waves with two different amplitudes are shown in figure 910. In other words, amplitude is the distance from the rest position to a crest or a trough. So how do you measure amplitude on a longitudinal wave? Well, look back at figure 9.5. Here you go. And notice the rest position indicated in the coils that haven't received the wave of energy. So here we go. Here's our rest position right here. The amplitude of a longitudinal wave is the maximum displacement of a point or coil in our slinky analogy from its rest position. So if you look at the compression and the rarefaction areas, notice how the coils have moved relative to a rest position between each individual coil. It is much easier to measure the amplitude of transverse waves because we can see it more clearly. The important thing for you to remember is that amplitude is the displacement of the medium from its rest position. Again, so from its rest position, the amplitude is here to here, the crest, or here to here, the trough. One other important thing to remember about amplitude is that the more energy a wave has, the greater its amplitude. So what do I mean by that? Say you and a friend were each holding the end of a jump rope and you wanted to shake the rope up and down to create a wave with a large amplitude. To do that, you would have to add a lot more energy, shake harder to achieve a higher amplitude than if you produced a wave with a low amplitude. Frequency and period. Suppose you are again wading in the ocean at the beach. The wave frequency indicates how many wave crests hit you each second if you simply stand there and do not move. So look at this figure. The black lines indicate each second that passes. The wave shown in the top image vibrates one complete cycle from crest to crest. So we measured from crest to crest, so that's one complete cycle in 1 second. So we have from here to here is 1 second. The wave shown in the bottom image vibrates 2 cycles from the crest on one cycle through the crest of the next and to the crest that starts the third cycle in 1 second. So frequency is the number of complete cycles in a given time. So here we go. We said from crest to crest is 1 cycle. So we have 1 here and 1 here. So the frequency here is 2. The frequency here is 1. For waves like those shown in figure 911, the frequency is the number of wave cycles that pass a point in a given time. Frequency is measured in cycles per second. So 1 cycle per second is 1/second. The frequency unit is often referred to as a Hertz, Hz, in honor of the German physicist Heinrich Rudolf Hertz, who discovered radio waves. Notice how the waves in figure 911 repeat each second. For the 1 Hertz wave in the top image, the motion starts at the crest, dips down through the rest position to the trough, then back up through the rest position to the crest again. It repeats the same vibration in the next second. Any motion that repeats at a regular time interval is called periodic motion. The time it takes to complete 1 full cycle is called the period. For the ocean waves hitting you while you stand in the water on the beach, the period would be the time between the crest and the next. You've already seen what a wavelength is, but let's look at it a little bit more. Wavelength is the distance between a point on one cycle of a wave and the same point on the next cycle. Since wavelength is a distance, it is measured in meters. In transverse waves, the wavelength is often measured from the crest of one cycle to the crest of the next, or from one trough to the next. In longitudinal waves, the wavelength is measured from one compression to the next, or from one rarefaction to the next. Notice the waves in figure 912. The top wave has a long wavelength, while the bottom wave has a shorter wavelength. Notice that when the wavelength is shorter, crests are closer together. So here we go. This is a long wavelength. So from the top of a crest to the top of the next crest is one wavelength, versus down here, the top of this crest to the top of this crest is a much shorter distance. In other words, waves with shorter wavelengths have greater frequencies. Thus, frequency and wavelength are related. Think about standing in the ocean at the beach again. If the wave crests are far apart, not very many of them will hit you in a second. If the wave crests are close together, several of them can hit you each second. So when wavelength is large, frequency is small. And when wavelength is small, frequency is large. So in other words, wavelength and frequency are inversely proportional to one another. When one gets large, the other gets small. It so happens that frequency and wavelength are related to one another through the speed of the wave. Remember from Module 6 that the speed of an object equals its distance divided by its time. Well, you can calculate the speed of a wave if you know its wavelength, which is the distance in meters, and its frequency, which is the number of cycles in 1 second, which is time. So let's look at this equation. Speed equals wavelength times frequency. In this equation, F represents frequency of the wave. V stands for the speed at which the wave passes a given point. Remember that physicists use the symbol V to represent both speed and velocity. Since frequency does not depend on the direction in which the wave is traveling, this equation refers to speed, not velocity. The funny-looking symbol, this guy right here, lambda, is the lowercase Greek letter, lambda, and it represents, as you recently learned, the wavelength. All right, let's have an example. One end of a rope is vibrated to produce a wave with a wavelength of 1.2 meters. The frequency of the wave is 3.3 hertz. What is the speed of the wave in meters per second? So step 1 is always write the list of knowns and unknowns. We have the wavelength is 1.2 meters, the frequency as 3.3 hertz, or 3.3 times 1/second. And then the speed is what we're trying to solve for. Step 2, write out the equation. Speed equals the wavelength times the frequency. Steps 3 and 4, substitute the numbers and solve. All right. The speed of the wave is 3.96 meters per second. Example 9.1b. What is the frequency of a wave that travels at a speed of 3.0 meters per second and has a wavelength of 0.5 meters? So the wavelength is 0.5 meters. The frequency is what we're trying to solve for, and the speed equals 3.0 meters per second. Step 2, write out the equation that we need. So here we have the speed equals the wavelength times the frequency, but we need to rearrange it to get the frequency equals the speed over the wavelength. Not sure why that random lambda is there. Step 3 and 4, write out the equation substituting the numbers from step 1 and solve. So 3 meters per second divided by 0.5 meters leaves us with 6.0 1 per second, or 6.0 hertz. Physicists typically like to use hertz instead of 1 per second for frequency, so the answer is 6 hertz. And what does that even mean to you? Well, it means that if you stand in the midst of the wave, 6 crests will hit you every second. On your own, 9.3, how does the amplitude of a wave relate to the wave's energy? The more energy a wave has, the greater its amplitude. On your own, 9.4, a longitudinal wave is suddenly stretched so that its wavelength is increased. If the speed of the wave does not change, what will happen to the wave's frequency? So again, wavelength and frequency are inversely proportional to one another. So if the wavelength increases, frequency will decrease. On your own, 9.5, suppose you are waiting on a beach that is experiencing waves that move with a speed of 0.5 meters per second and have a wavelength of 0.25 meters. If you stood still, how many waves would hit you every second? So again, what do we know? The wavelength is 0.25 meters. We don't know the frequency, and we know the speed is 0.5 meters per second. Write out the equation. We have the speed equals the wavelength times the frequency. And once again, we need to rearrange. So we have the frequency equals the speed over the wavelength. Step 3 and 4, write the equation, substitute numbers, and solve. So we have 0.5 meters per second divided by 0.25 meters, which gives us 1 per second, or 2 hertz. So what does 2 hertz mean? If you stand in the midst of this wave, 2 crests will hit you every second.